Hello and welcome to my Neuromatch talk, where I will be testing ideas about memory replay and consolidation in the human brain using an artificial neural network. We know that when we are resting or asleep, the experiences we have had the previous day are reactivated in the brain, and this is known as memory replay. We also know that when we wake up, our memory for these events is improved. Therefore, replay helps us to consolidate memories. We know less about how we consolidate category knowledge. We can see many examples of a category every day. However, it does not seem efficient to replay every single example. We have no HD video in our head to play back all of the day's events anyway. Nor does it seem adaptive, as the goal of category knowledge is to be able to recognize a completely new example. We propose that it will be more efficient to replay an imagined prototype of that category based on the features we have learned. In this example, we would replay a novel truck based on what we have learned so far about trucks, which reduces the demands on memory. A second question we would like to answer relates to where replay is functionally relevant in the brain. Replay originates from the hippocampus and targets many brain regions, including the ventral visual stream, an information pathway which supports category knowledge. However, it is difficult to relate this replay directly to the key neural changes which support memory improvements. It is not clear in which one of these target regions, circled in yellow, that replay is most effective. One way we can approach these questions is to harness the power of deep convolutional neural networks. Pictured is the architecture of the VGG16 network. This network is able to process input images and classify objects within to an accuracy level comparable with humans, and the representations it extracts bears a close functional correspondence with those extracted by specific brain regions along the ventral visual stream. We can simulate the replay of imagined prototypes of a category in this network by capturing the relationships between neurons in a particular layer of the network and then sampling from a point in this space. The resulting activation is what would be a typical activation for the network at this location for a particular category based on what it has learned so far, but not exactly what it has seen before. Thus, the activation represents a dream-like concept constructed from past experience. The network then processes this novel activation during offline periods. This can be performed at any location in the network, with example locations provided here. By simulating replay at these different locations, we can answer how granular replay representations need to be. Replaying representations from earlier in the ventral stream would be more taxing, and perhaps one would not want to make too many modifications to these early visual areas which extract basic features. Our major question then was whether the brain replays such dreamlike representations and where would this be most effective. To simulate the learning and consolidation of new categories, we took a pre-trained VGG16 network equivalent to a fully functioning human visual system and tasked it with learning 10 categories it had never seen before over 10 days. During nighttime periods, we implemented replay. Replay helps the network recognize new examples it had not seen before in a generalization test, but this was most effective when performed towards the end of the network, in an area corresponding to the lateral occipital cortex. Having answered where in the ventral visual stream replay is most effective, we then try to find out when during learning replay is most effective. Most replay studies just look at neural reactivation in the hours following learning, but category learning can take a lot longer than that. So we extended training from 10 to 30 days and compared generative replay over time to a network which did not replay its memories. Once again, this is the performance of the network on a brand new set of unseen category exemplars to test if it can generalize what it had learned. We found generative replay was most effective following the acquisition of recent knowledge, suggesting we do not replay remotely learned events often. We also compared generative replay with veridical replay, the unlikely scenario whereby we could replay every single category example we have seen, like having a HD video of the day stored in our brain. Surprisingly, generative replay was as efficient, making a strong case that this is the form that category replay takes in the human brain. We were also curious to find out what happens if you have limited exposure to a category and how much replay could compensate for that. Therefore, we trained the network on real images for just one day, with continuous replay for 29 days and nights, and we can see that the network still reached an adequate level of performance, although not as high as when learning and replay are interleaved. So the brain does not necessarily need to replay all category examples, but how does it decide which categories to replay? There is a well-documented phenomenon in sleep consolidation research, and that is that it benefits information which has been weakly learned, and those experiences are actually replayed more often. This suggests some categories are replayed more often than others, but it's not understood how the brain manages to selectively replay and consolidate this information. We propose this may be an interactive process between multiple brain regions. We know that the hippocampus is heavily involved in the replay process, and we hypothesize that this region may select replay events in the neocortex and receive feedback on that selection. We therefore created a side network to perform this function, which would select one category at a time for replay and learn through reinforcement which were the best categories to consolidate. The goal of this side network was not to improve the overall performance of the main network, which remained unchanged. Rather, looking at individual category performance, we can see that weak categories, those which were originally quite difficult for the main network to learn, were chosen more often by this side network, and their performance improved. However, this came at a cost, with originally high-performing categories being chosen less and being consolidated less. We propose a mechanism like this may rebalance experience in the brain, resulting in a more even performance across category knowledge. In summary, using a human-like neural network, we present a strong case that consolidation of category knowledge may be achieved by replaying dreamlike prototypical representations, thus alleviating the demand on memory resources. We propose the key neural changes which take place to facilitate consolidation happen in the lateral occipital cortex. We also reveal that replay is likely to help us consolidate more recently acquired information. Finally, we present a candidate mechanism for how the brain consolidates weakly learned information in the form of multiple interactive neural networks. Finally, I would like to thank Professor Brad Love and the Love Lab for their support, advice, and ideas throughout this project. Thank you also to our funders, the Wellcome, the Royal Society, and the National Institutes of Health.